Okay, so this is the extra session that we have from chapter 2. We're going to be discussing infinite sets. In the book, this is chapter 2, section 5, which is nominally about the cardinality of sets. So I'm not sure why when I do the presentation here, there's a bit of the previous slide that comes up. So when there's something that comes out at the bottom of the previous slide, I guess it will appear there. So here we talk more about cardinality. So cardinality is nominally the size of the set. So how many elements are in the set? So here we have the distinction of finite sets. So a set is finite with cardinality n if there is a bijection. So uh, remember from functions that bijection is a one-to-one correspondence. So basically, you're listing the elements. Now, I'm not sure why in the book this is numbered from 0 to n minus 1. It would be more natural to list it as 1, 2 to n. But I guess that's aligned to, say, C++. So you can put it in an array of size n where the index goes from 0 to n minus 1. So that's one way to think of it. If you can place each element to one of the elements as an element of the array with one of the indices from 0 to n minus 1, then we say that that set has cardinality n. So again, the bijection is a one-to-one and onto correspondence. For each index, there's an element of the set. For each element of a set, there's an index. And there is no double map. Of course, each index is only mapped to one element, and one element of the set S, and S is mapped. Each element of S is mapped to only one index. Okay, so a set is infinite. Again, we've seen this before. Infinite is defined, or in this case, a set is infinite if it is not finite. So basically, it's the definition of the word infinite in this case, wherein the prefix means not. We also see that with later on with the word uncountable and countable. So we'll see that when that comes out. So we already know that n is an infinite set, mostly because there's no way to map each of the elements of n. There's no way to index it because there's more than, for any number n, there's more than n counting numbers, more than n natural numbers. So the sets A and B have the same cardinality. So we denote the cardinality using this size of operator. So the size of A is equal to the size of B if and only if there's a one-to-one correspondence. So this crucially comes after the section on functions. So you really need to define, in order to define two sets to be equal to each other in cardinality, you have to define a bijection between them. So this, strictly speaking, isn't entirely necessary because the other way of doing it is to show that uh, the size of one is less than or equal to the other, and vice versa. If you show that, then you can show that they have to be of equal size because it can't be the case that one is larger than the other and the other is larger than the first. And that's also through functions, as we'll see later on. So if there's a one-to-one function from A to B, the cardinality of A is less than the cardinality of B. So again, what's one-to-one? One-to-one is if you have if two images are the same. So if you have two elements of A and their images under the function f, so f of A is equal to f of B, then that's only possible if A is equal to B. So that means that for every image in the codomain, only one element of the domain maps to that. That's what we consider one-to-one or injective. So in that case, for every element of A, there is an image of B. There's an image in B. So that means for the image of the set A is a subset of B. So that indicates that the size of A is not more than the size of B. The size of the domain. So for a one-to-one function, the size of the domain cannot be larger than the size of the codomain because every image in the codomain has a unique pre-image. So for every element of the domain, there is a unique image. So you can think of it as there's a copy of the domain in the codomain. There could be elements that are not in the codomain, not in the range, sorry. Not in the range, but inside the codomain. So that's the reason why it's possible for the codomain to be larger. So when the cardinality of A is less than or equal to the cardinality of B, and they have different cardinalities, then obviously the cardinalities cannot be equal. So it must be the case that the cardinality of the smaller set is strictly less than the cardinality of the larger set. Okay, so we have what's referred to as countable sets. So a set that is either finite or has the same cardinality as the set of positive integers is called countable. So that's why I referred to n as the set of countable numbers. So n is a countable set because obviously there's a one-to-one map between the positive integers and the positive integers in the identity map. So if it's finite, then that means there is a subset of the counting numbers that can be mapped to that set. I actually probably shouldn't say that because, as we'll see later on, some subsets of, well, we already know that some subsets of the set of positive integers are infinite. And we've shown that they are countable. So like the set of prime numbers, the set of even positive integers, those are countable sets and those are not finite. So a set that's either finite or has the same cardinality as a set of positive integers is called countable. So that example itself actually kind of shows you one of the weird things that happens if there's an infinite set. It's possible that an infinite set has a subset with the same cardinality. That is, you can show a one-to-one correspondence. We showed that there's one-to-one correspondence between the prime numbers and the set of counting numbers because you can list the prime numbers. And there is no number in which that stops. So that means that you can keep going into the dot 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 of the set of natural numbers, and you'd still find a prime number that's mapped to it. Obviously, the prime number has to be larger than the index, but it doesn't mean that either of them stop. So that's kind of the weird, the mentally warping thing about infinite sets is that the subset of an infinite set can itself be infinite and of the same cardinality, because that doesn't seem sensible in, for finite sets. For finite sets, a finite set cannot be the same size as a subset of it that doesn't contain all of the elements. If you have n elements and you take a subset that doesn't contain one of the elements, it can only have n minus one element. So they can't have the same cardinality. One is strictly less than the other. But with infinite sets, it's possible to show by one-to-one correspondence, by bijections, that some the infinite subsets of the set of counting numbers, natural numbers, is the same size as the set of counting numbers, even though you're not adding all of the elements. Like every even number, for every even number, you just need to have a map uh, from z to 2z. 2z is usually how you describe multiples. So 2z is all of the multiples of 2, 3z is all the multiples of 3. And you can easily show that f of n is mapped to 2n is a bijection. So it's onto this set. For every even number, if you divide it by 2, you get the pre-image. And then you can show that it's one-to-one. For every index, you get a different even number. Every even number has an index, and every index is mapped to a unique even number. So that means that it's a bijection, and this map shows you that the set of even integers is positive even integers is the same as the size of, sorry, should be z plus, but that actually kind of works even for integers and even integers. The set of counting numbers, the set of natural numbers, has a bijection with the set of all even positive numbers. Okay, so a set that is not countable is called uncountable. This is what I was referring to. Basically, the definition of the prefix un in this case. So in this case, not countable is uncountable. But it kind of belies the whole idea. So you're saying that there are sets that are not finite and does not have the same cardinality as the set of positive integers, which already implies the thing that we mentioned before that Cantor discovered, which is there is more than one type of infinite set. Well, there's more than one size. If you're speaking of size in terms of cardinality, there are infinite sets that have different cardinality. So that took him about 17, 18 years to try to figure out, because he was able to basically get the framework for most of the discussion here on different countable infinite sets. Like set of primes is countably infinite. The set of even integers uh, is countably infinite. The set of integers is countably infinite. The set of rational numbers is countably infinite. So basically, he spent a lot of time trying to figure out if every infinite set that he can describe is countable. And then he found an example that wasn't. And surprisingly, it wasn't the set that we normally think of as uncountable. Because the easiest set to describe as uncountable is the set of real numbers. There is something in the set of real numbers and the set of rationals that's common, but there's still something missing between them. So, not discussed here. One of the concepts that's necessary for approximation that was given in calculus is that the set of rational numbers is dense amongst the real numbers. So if you have the set of all real numbers, there's always, for any type of error, for any approximation error that you can think of, there's always a rational number within that error of that irrational number, of that real number. If it's a rational number, then obviously the error approximation for itself is zero. You can always choose a rational number to approximate itself, the error would be zero. But for an irrational number, you can always choose a rational number that's close enough. Do you need something that's correct up to 6 decimal places? You can find it. You can find an infinite number of them. If you need something that's correct up to 12 decimal places, you can find it. No matter how small the error is, you can always find a rational number that is within that error of an irrational number. That's kind of the foundation of the approximation theory that's given in calculus. So, yeah, something that's not here because it's not exactly discrete mathematics. Okay, so this is what I was describing before, the Hebrew letter Aleph. When an infinite set S is countable, the cardinality of S is said to be Aleph null. So that is the cardinality of the set of natural numbers. So the set of positive integers is a countable set, same as with the evens. Basically, just the map of f f of n is 2n minus 1. So if n is the set of positive integers, so 1 is mapped to 1, 2 is mapped to 3, so on and so forth. So again, every odd integer you can solve for the index. Every index gives you a different odd positive integer. So 1 to 1 and on to. An infinite set is countable if and only if it's possible to list the elements. So whenever we do a list, so we say that it's sort of like we're writing it down. So we're numbering it from 1 to so on and so forth. So 1, 2, 3, 4, 5, 6, 7, so on and so forth. That's the same thing as writing them in sequence. So when you write them in sequence, you're implicitly writing them as A1, A2, A3, A4, dot, dot, dot. So the index is the element of the set of positive integers that you are mapping to that to A1, to the element of the set. So if you can exhaust all of the elements of the set in this sequence, without repetition, you're implicitly making a bijection. So we've already seen that z is countable, so this requires a piecewise function. So we let uh, n divided by 2, n be mapped to n divided by 2 if n is even, and 1 minus n over 2 if, oh, yeah, 1 over n minus 2 if n is odd. So this gives us the sequence 0, 1, negative 1, 2, negative 2, 3, negative 3, dot, dot, dot. So to show that this is a bijection, obviously all of the elements, you have to separate n between the even and the odd. So amongst even, they're all mapped to different even number, to different positive numbers. Amongst the odd n, they're all mapped to different odd numbers. So that means that it is a one-to-one function. And then you show that if it is a positive integer, it has to have an even index. If it's a non-positive integer, it has to have an odd index. So that would give you one-to-one and onto. So that would be a bijection. So I didn't mention this. So I will, when I upload this video, I will connect it to the TED Ed talk on Hilbert's Hotel, which was the thought experiment model that David Hilbert devised to try to describe these infinite sizes. So Hilbert's Hotel has an infinite number of rooms. It's numbered from 1 to so on and so forth. So it's effectively a listing. And then you have people coming in and they have IDs on them. So the IDs are the numbers that you want to put into the sequence. So your goal is to, for every guest that comes in, you want to give them a room. So obviously, no two people should be in the same room. And, Hilbert's Hotel prefers to be full all the time. So I'll link to that, and then I'll look for other videos. I think either amongst the TED Ed videos or the 3B1B videos. I don't think 3B1B does discrete mathematics though, so I'm not too sure that's going to come out. So in the case of Q plus, so the usual way in which this is proven shows you that you can get a set larger than Q plus, in the sense that instead of having a 1-to-1 and onto map, you're basically going to show that there's an onto map that is not necessarily 1-to-1. So you can have multiple rooms assigned to the same, multiple indices mapped to the same number. So how does this work? So, okay, so I think I should make a little more space. Okay, so here's the idea. So what you do is you write a table. So you have a table where the columns are numbered 1 to so on and so forth. Let's write a few more, 5, dot, dot, dot. And then the rows are also numbered in that way. And then the columns determine for every entry in the table, the column number gives you the numerator and the row number gives you the denominator. So this is 1 over 1, this is 1 over 2 over 1, 3 over 1, 4 over 1. Doesn't really matter if it's numerator along the columns and denominator along the rows or vice versa. This will give you, basically a flipped image of the same table. So the first row is all positive integers. So obviously they should be there. And then you have 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, and then 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3. So obviously, in this table, you have all rational numbers, because all rational numbers, in this case positive rational numbers, are numbers where the numerator and the denominator are both positive integers. just happens that in this model, there are multiple versions of, say, 1. 1 is 1 over 1, and 2 over 2, and 3 over 3, so on and so forth. In fact, every positive rational number appears multiple infinite times in this case. Basically, you have the version in lowest terms, and then you have the version with lowest terms times 2 over 2, lowest terms times 3 over 3, and so on and so forth. So this is, if I can map all of the elements here, if I can put it to an index, so if I list them in a sequence, then it would be onto but not one-to-one, which actually means that the set of counting numbers has to be larger than the set of, well, technically the cardinality of the set of counting numbers would be greater than or equal to the cardinality of the set of rationals. And then they would be equal because the set of counting numbers is among the rationals. So that easily makes them equal. So in this case, after you list them this way, what you do is you just make an algorithm so that you can go through each of the numbers, which is really just, okay, start with 1 1, and then you separate them into diagonals, and then you go from one diagonal to the other. So from the first diagonal, you go to the next number, so 2 1, and then you go along the diagonal until you go to the end. So first, second, third, and then the fourth would be 1/3, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th. So you can actually determine which index goes to part of the which part of the table. So if you'll notice, the number, so once you finish a diagonal, you would have finished a triangular number of numbers. So triangle numbers are basically the number of dots required to fill in a triangle of a particular size. So there's 1, and then there's 3, and then there's 6, and so on and so forth. So if you know which diagonal a particular number appears, which you can figure out. So, for example, every number on the same diagonal has the same sum for the numerator and denominator. So you just need to check. So 7 over 6 is on the 13th diagonal because the sum of the numerator and the denominator is 13. So that means that you just need to figure out where does the count start for that diagonal. So you just add the first 12 diagonals. So that would be T12, the triangle with 12 dots on each side. So Tn is basically n times n plus 1 over 2. This is the sum of the first n positive numbers. And you already know this formula from Math 200. So I from 1 to n is Tn. So for a number on the 13th diagonal, you'd start with T12, the sum of the first 12 diagonals. That would be 6 times 13, which is 78. And then you have, so 1, 2, 3, 4. Each of the diagonals has, so if it's the nth diagonal, there are n numbers along that diagonal. So that means that any number on the 13th diagonal would be numbered from 78 plus 1 to 78 plus 13. It's just a question of where does it start. So you can figure it out from, it's kind of a repeated sequence. So for each of the even diagonals, you're going from top right to bottom left. For each of the odd diagonals, you're starting from bottom left to top right. So if it's bottom left to top right, then you're starting with numerator at 1. If it's from top right, it's at denominator is 1. And then you increase one and decrease the other. So either you increase the numerator while decreasing the denominator, or vice versa, depending on which direction you're going. So you can figure out which index goes for each number. So in that case, that gives you a for this set of numbers. So without reducing it to lowest terms, that gives you an onto map. An onto map is actually sufficient in this case. So that means that every number in this table gets an index. It just happens that an infinite number of the same number is uh, is mapped to the same positive rational number. So in that case, it's not exactly a bijection, but it's sufficient to show that there is an onto map, which indicates that the cardinality of the domain is greater than or equal to the cardinality of the codomain, because every element of the codomain has at least one pre-image. And since we already know that every positive counting number, positive integer, is a positive rational, that means that that is contained in the set of rationals. So the only way that can happen is if they're the same cardinality, which in this case is Aleph null. So the crucial aspect of this is R is not countable. So I don't think that, well, okay. When Cantor discovered that there were sets that were infinite and not countable, it wasn't R that he discovered. But the proof for showing that R is not countable is basically the proof that he's using for showing that the set that he did show doesn't have the same size. Doesn't have the same size. So, so whenever you're trying to prove something that is the negative of something, like to show that the primes are infinite, or in this case to show that R is uncountable, you'll need to do a proof by contradiction. So that means that like what we did with the primes. So what we did with the primes is that we assumed that the number of primes is finite, and then we showed that if we had that assumption, we can make a prime that's not listed. So in this case, uh, the proof that that's usually given for showing that R is not countable is not for the entirety of the real numbers. In fact, usually what's shown is that you can show that the, actually not even including one, the the interval, I guess it's fine to include one, because uh, you'll need to include the real number 09 bar. So in this case, we're assuming that 1 is represented by 0 followed by an infinite number of nines. So usually what's shown here is not that R is uncountable. A subset of R is uncountable, which is just the interval from 0 to 1 is uncountable. Okay, so how is this done? So to show something like this, like to show that something is infinite, you assume that it's finite, and then you show that that gives you a contradiction. There is a number that's not in the list. So you assume that there's a complete list. So if it's finite, I can index them from 0 to the number of primes. And then you can show that there is a prime that's not in that list. Same thing for uncountable sets. You list them in a sequence. So let's say that all of the real numbers from 0 to 1 can be listed A1, A2, A3, dot, 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 so on and so forth. So assume that 0 to 1 is countable. So every real number between 0 and 1, including 0 and 1, is in this particular listing. Okay, so how do we show that that's not the case? So if you do that, then so instead of writing A1, I'll just write the indices. So if the indices are 2, 3, 4, 5, 6, so on and so forth. So let's say the first number is 0.50000000. I'm going to write out, if it's a terminating decimal, I will write out all the zeros. So basically, each of the real numbers can be listed with an infinite number of decimal places. And it's required because I can't really do this without that. So let's say 3141596. So pi divided by 10. 2718. I can't remember what the rest of the numbers are. So e divided by 100. Uh, Repeating decimal. So it's not necessarily this list, but we'll show the process that we're going to use to determine a number between 0 and 1 that is not on this list. That's the requirement. To show that it's not countable, we assume that it's countable, and we can always show that there's something that's not in that list. So 4, 2, 4, 5, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 1, 0, so on and so forth. So let's say this is the start of the list. So we'll construct a real number between 0 and 1 that's not on this list. So what we do is for the nth number, we look at the nth decimal place. So as you go down, you're just looking at that diagonal entry. That's why this is often referred to as Cantor's diagonalization technique. So we look at the diagonal entries. So for the nth element, we look at the nth decimal place. So there's a number there. We're not going to collect that. What we're going to do is we're going to change it. So for every digit here, there's 10 possible digits that you can use. So instead of 5, let's say we move it up by 1. So it becomes 6. 1 becomes 2, 7 becomes 8, 3 becomes 4, 0 becomes 1, 0 becomes 1. If it's a 9, it becomes a 0, and so on and so forth. So, okay, so we can construct digit per digit a real number. Now, the claim is this real number that we constructed by construction is not in the list. That's what we need, right? We need a real number that's in the interval from 0 to 1. This is definitely a real number within the interval from 0 to 1. And that number is not in the list. Why? Because if this was the nth entry, we already know what the nth entry is. We look at the nth decimal place. They have to be different because we constructed it so that they would be different. So this cannot be the same as the first number because they differ in the first decimal place. This cannot be the second number because they differ in the second decimal place, and so on and so forth. So for every real number in the list, this cannot be that real number because it differs in at least one decimal place. So it cannot be any of the numbers in the list. But by construction, this is just a number between 0 and 1. So we found a real number that is between 0 and 1 and is not in the list. And it doesn't matter which list you choose. For any type of listing, you can always find a number that's not on the list. So therefore, it's not possible to make a listing of all the numbers between in the interval from 0 to 1. So since it's not possible to make a list, that means that the set of all real numbers from 0 to 1, including 0 and 1, is not countable. That's it. That's all you need to show. So that uses what's referred to as Cantor's diagonalization technique. So note that this was not the set that Cantor saw was of a different size, but his technique can be used to show that a set is uncountable. Okay, so there's some theory that goes about this. So if you have two sets that are countable, then the union is also countable. Basically, in this case, uh, you can use odd and even integers, and then you'd have a map that is onto. So since the map is onto, so basically, if you have all of the elements of A, B, A1, A2, dot, 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 and then all of the elements of B, B, B1, B2, you just write the list A1, B1, A2, B2. And that would be a list. Now, the thing is, it's possible that the intersection is not 0. So what would happen here is you'd have a sequence where you have some repetition. That's equivalent to making an onto mapping from the set of counting numbers to the set A union B. And in that case, since we know that A is in A union B and B is in B union B, that means that uh, the cardinality of this set has to be greater than or equal to the cardinality of A. This shows you that the map is same cardinality as the set of naturals, and since these are countable, uh, well, I'm assuming they're countably infinite. If either of them is finite, then it should be easy to show that that the union is countable. Whether or not it's countably infinite, if one of A and B is countably infinite, or it's finite if both of them are finite. So assuming that they're both infinite sets, you can show this basically from this sequencing. So if A and B are sets with A has cardinality at least not greater than B, and B has cardinality not greater than A, then the two sets have to have the same cardinality. So this is basically the same as showing this would be if you had a map that is onto. This would be if you have a map that is 1 to 1. Or you can have, since you're doing two maps anyway, you can have, this could be the same as a map from B to A that's 1 to 1. Or this is a map from B to A that is onto. So basically, as long as you show one combination of this, either these two different Fs, so F1 and F2, and then J1 and J2, you can show that you don't need to show that it's a bijection. Basically, just show two mappings. So that is one of the descriptions. So we can basically show that adding a single number to two different uncountable sets does not change the cardinality. So the only difference between this set and this set is the number 1. And basically, since we already know that one of them is uncountable, we just need to show that the other one cannot be countable. So not interesting enough to try to work out the details in this case. So let S be a set. An enumeration of S is a surjective function f from an initial segment of n, an initial segment of n. So basically sub uh, a finite subset. So from 1 to m. An enumeration of S is a surjective function. So it doesn't need to be a one-to-one correspondence. It just needs to map onto S. So every element of S has at least one preimage. If F is injective also, then F is an enumeration without repetitions, otherwise it's an enumeration with repetitions. So if it's also injective, then it's a one-to-one correspondence, and the size of the subset of N is the cardinality of S. Otherwise, it's an enumeration with repetitions. So if you have this set, then this sequence is an enumeration, and this sequence is also an enumeration, but in this case, it's an enumeration with repetitions. So this is without repetition. Notice that the sequence is of length 4 and S has cardinality 4. So this is also an enumeration without repetition. There's only 4 elements. Okay, so I think that's missing here. So the last statement there is S is countable if and only if there exists an enumeration of S. So that seems to make sense. That lessens the requirement, because before the requirement was a bijection. If you don't need to know the actual cardinality and you just need to know that it's countable, you just need to show that there's some sort of enumeration. So for example, if you have an alphabet with two characters, A and B, the set of strings, basically concatenations of these two characters, including the empty string, which is usually called lambda, is countably infinite. So how do we do that? Uh, how do we do that? So what we do is, instead of using A and B, so let's say A is, for every string in here, for every string in there, we map it to a bit string. So the bit string starts with 1, and then every A is 0, every B is 1. So you prepend a 1, and then you translate all the A's to 0, all the B's to 1. So that means that every string is mapped to a bit string, and the 1 at the start basically adds a power of 2. So what would happen is you'd have a unique, you have to prepend it with a 1, because if you leave it B, let's say you have A, B, so lambda, A, B, uh, A, A, B, B, A, B, B. So if you just directly translate, this is just 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. 0 would map to 2 of the numbers. So if you prepend a 1, so this becomes 1, this becomes 2, this becomes 3, this becomes 4, this becomes 5, this is 6, this is 7. And you'd have a natural mapping between all of the natural numbers and their binary representations. And then the binary representations map to each of the strings with 2-bit strings, with two, in a 2-character alphabet. So you can actually also do this with any finite sized alphabet. You just move from binary to n-ary. So it's base n numbers. You just do the same map. In that case, you don't actually include all of the numbers. So more results. Every infinite set contains a countably infinite subset. So what you just need to do is you just need to push one of the elements into a list. So it's possible that the list isn't exhaustive. So if it's uncountable, you'll have some numbers left over, no matter what listing you do. If it's a countable set, then it's also possible that you'll leave things over. So for example, for the set of integers, you can just choose the positive integers. You're not touching any of the negative integers or 0, but definitely it contains a countably infinite subset. The union of a countable collection of countable sets is countable. So in this case, same rule that we did for uh, the rationals. So in that case, let's say you list all of the elements from 1 to infinity, and then you list all the sets from 1 to infinity. So you have a table of the first element of the first set, second element of the first set, third element of the first set, being the same column. Sorry, being the same row or column, doesn't matter. All of the elements of the same set are in the same row or column, and each of the other direction gives you the elements with the same index. And then you just do that slithering along the diagonal. That will give you a countable set. That will give you a map that's countable. So again, in that case, it would be an onto mapping under the assumption that the intersections are not necessarily empty. So it doesn't need to be disjoint. You'll just have different indices, multiple indices for the same entries. So if sigma is a finite alphabet and sigma star is a set of all strings over sigma, then here is the thing. Okay, so this actually comes early here. Remember what P is? P is the power set. It's the set of all subsets. The set of all subsets of the set of all strings is uncountable. That is actually the thing that Cantor discovered. So let's see if there's a more general. I'm actually not sure there's a more general description here. I think this might be it. This is the thing that's required. So so the thing is, what you do is you have subsets of the set of all strings. So the power set is the set containing all the subsets of this set. So the power set of A is the set containing all subsets of A. So to show that it's uncountable, we have to do contradiction proof again. So we assume that it's countable. So we can list all of the subsets. So S1, S2, S3, S4, S5, so on and so forth. And then you have all of, we already know that if you have a finite alphabet, this is countable. So we write all of the possible strings. We list them. So it's possible to enumerate them because this set is countable. So let's say capital S for set, small s for strings. So we list all of the strings S1, S2, S3, S4, S5, so on and so forth. So that could be the natural map that we have, but in any case, it's some mapping. So in this table, we list just a binary digit, either 1 or 0. So we know that every subset can be written by a bit string. Basically, we determine the bit string that denotes this particular set. So for this set, it contains S1, doesn't contain S2, contains S3, contains S4, contains S5, and none of the others, so on and so forth. So let's say this is the actual set sigma star. So it would be ones. Let's say this is the empty set, so this would be all zeros. This would be 1 0 1 0 1 0 1 0. This could be 1 1 1 1 0 1 1 1, so on and so forth. So again, we do Cantor's diagonalization. We choose the diagonal entries. So for the ith set, we look at the ith string. So since the ith set, so the first set contains S1, we construct a set that does not have S1. So since S1 contains string 1, we choose a set that doesn't contain string 1. Doesn't contain string 2, contains string 3, contains string 4, contains string 5, and so on and so forth. Like with the diagonalization for real numbers between 0 and 1, this constructs a set that cannot be in the list. So the set S is not amongst the sets that are listed here. Obviously, it's a subset of the set sigma star. It cannot be one of the listed sets because if it was S1, it would contain string 1, but it doesn't contain string 1 by construction. It can't be S2 because S2 contains string 2, but by construction, this set doesn't contain string 2. It cannot be S3 because S3 doesn't contain string 3, and this set by construction does contain string 3. So in this case, we just flip the bits. We got a bit string that is of infinite length that is different from all of the bit strings here in at least one bit. And that is how you show that there is always a subset in the power set that is not in the list. So that's actually what Cantor proved. The power set of a given set has to have more elements. The cardinality cannot be the same. So strictly speaking, if you have a set, the cardinality of the set is always less than the cardinality of its power set, even when that set has an infinite number of elements. And here's the thing. It's also true if S is uncountable. Although it's a little harder to prove in that case. You need an indexing along the uncountables. But the basic method is still the same. You're doing a diagonalization and constructing something that is not mappable. So it cannot be the same size. So a set S of cardinality C is of cardinality C if there's a bijection from 0, 1, which we know is uncountable, to S. It's generally considered that the set of real numbers has the same cardinality as 0 to 1. So sets S and T are equipotent, so they have the same size if there's a bijection from S to T. So this is the general proof, the general method in which we show that two sets have the same cardinality, so that they're equipotent. So equipotence is an equivalence relation over any collection of sets. So basically, you just have a representative set that represents all of the sets of that particular cardinality. So technically, you're only looking at the cardinality. So all of the sets with 5 elements are equipotent. 5 fingers on my left hand, 5 fingers on my right hand, 5 toes on my left foot, 5 toes on my right foot, 5 members of a Sentai team, like the Power Rangers, for some variants of Power Rangers, 5 lions from, Voltron or something. So, uh, the set S has cardinality not greater than set T if there's an injection. So that's the one-to-one correspondence. The one-to-one function. Uh, S is okay. Can't read that. It's strictly less than. So they are not equipotent if there is an injection but no bijection. So as long as you can show that there's no bijection, which is not generally the way we prove it, it's kind of difficult to show the absence of anything. Okay, so here's the last slide here. This is actually the thing that comes from what Cantor discovered. So we have a set that is larger than the set that is larger than the set of counting numbers, and we have one of the sets that's larger than the set of counting numbers, which is the continuum. So let's say S is finite. Now, if S is infinite, then the cardinality is less than Aleph null. So this is actually an infinity that you can compare. We don't actually compare, say, infinity is greater than 8. That's not generally what we say, because this is not something that you can compare. Whereas here, that's a number that you can compare to this number. So that's the difference. That's the reason why there's a different symbol. That's why we call it differently. And it's also because we want to describe larger alephs. So if S is an infinite set, then its cardinality is at least Aleph 0. So this was what Cantor proved. The power set of a set always has larger cardinality than the set itself. So we can show that for countable sets. There is an equivalent way of showing it for uncountable sets, but it's a little harder to substantiate. The mechanism doesn't quite work, but the mechanism is analogous, but it's not exactly the same way. So here's the thing. Aleph null is the cardinality of n, and the power set of n is larger than that. Technically, this is Aleph 1. This is Aleph 2. So each of the power sets of n, power sets of n, have different cardinalities Aleph 1. This is the reason why we have Aleph null there, because Aleph 1 is the cardinality of the power set of n. Aleph 2 is the cardinality of the power set of n, and so on and so forth. So basically, that subscript tells you how many power sets you're employing. Each of them is different. So strictly speaking, Aleph I is less than Aleph I plus 1, and so on and so forth. Here's the problem. C is not in that list. Well, at least C is not directly shown as on that list. We know that C is larger than Aleph null, but we don't know how much larger. So there is a hypothesis in set theory that says that Aleph 1 is C. Basically, C, the cardinality of the continuum from 0 to 1, is the same as the cardinality of the power set of n. It has not been proven. It also has not been disproven. So that's why it's considered a hypothesis. And there's a number of theories. This is one of the hypotheses that's usually used, that you have to state that you're using it. Assuming the continuum hypothesis is true, or assuming the continuum hypothesis is false, you can make further conclusions. There's another one called the axiom of choice, which is not a hypothesis, but is generally considered as either something that you're allowing to do or not allowing to do in your axiomatic systems. So that's another one that's considered kind of like a hypothesis. You can't prove it or disprove it using the theorems of set theory. So in this case, this came from Cantor. He discovered that, yeah, okay, there is a set that's larger than Aleph null in size. And we know that the set of reals is larger than the set of counting numbers. What we don't know is whether or not that is the exact size as the next sized set. Nobody knows. And that's way beyond what we can do for this particular class. But it's useful to know that this is a frontier in mathematics. It's not proven. It's been more than 100 years. It's probably coming close to 150 years already. Still has not been proven or disproven. So there's still things that, as I may have mentioned before with Gödel, there's statements that are true. In this case, the statement could be Aleph 1 is equal to C, or Aleph 1 is not equal to C. At this point in time, it hasn't been proven. And according to Gödel, some statements can't be proven. Some true statements can't be proven. So in this case, coming up to 144 years since Cantor. And it was the century problem. So the equivalent of that was in 2000, the Clay Institute said that there were 7 problems that were considered millennium problems, the main problems in mathematics that needed to be solved. One of them has been solved already. And when it was solved, they made good on their promise, because their promise was, if you can prove or disprove this particular theorem, in that case it was the Poincare conjecture. If you can prove or disprove it, we will award you $1,000,000. And they awarded it. And the person who proved it didn't take it. The What was his name? Oh man, no, I'm forgetting the name of the guy. Uh, the guy who proved Poincare conjecture. I haven't discussed this in a while, so I haven't thought about that guy. But he's generally considered kind of a hermit mathematician, and truth to be told, he doesn't need anything else if all that he needs is, people in the future will talk about him. Because he was the guy who proved something that nobody could prove, even with an incentive of $1,000,000. So, uh, the continuum hypothesis is not one of the millennial problems because it's kind of difficult. So they've kind of veered away from it, but it's still an open problem. So, in terms of programming, there is an equivalent concept called computability. So a function is computable if there's a computer program in some programming language that finds the values of this function. So, okay, so I'll need to show the end of this. So, if finds the values of this function, otherwise it's uncomputable. So this is related to a concept in computer science called, there is a problem in computer science called the halting problem. So the halting problem is, for any given function, so in this case a program, in this case a function producing results, for any given program, there is a program that tries to determine if that program will halt or not. So that's kind of the problem with the halting problem. So it's obviously, if a program doesn't halt, then it cannot produce its results. So that's kind of the direct relation. So if there is no function that can produce, there is no function that halts and produces a result, then we can consider it a function uncomputable. So there is a correlation between that, kind of loosely. I don't want to go into details, and actually I've kind of forgotten what's there already. But it does have something to do with these countability of sets, in the sense that if you try to figure out what the cardinality of an uncountable set is. From a description, it might not be reasonable to figure if a function will know that it's uncountable or not. So given a set builder description. So that is something that can be considered an uncomputable um, problem. Whether or not figuring out whether or not from a description you can figure that uh, a set is countable or not. I think that's one of the descriptions, but I've forgotten. I apologize. It's slightly outside my field, but it should be something that you should be aware of. If you're interested in this uncomputability, you can read the last section, well, the fifth section of chapter 2 in the book, or you can read up on uncomputability and probably look up on the halting problem. So I'll probably put some links. I'll probably put a link to the Hilbert's Hotel video as well as anything related to this uncomputability concept. Okay, so that's the last slide from chapter 2. Uh, you may want to go over this after you've gone through functions if you haven't done it yet. So I know that one of the sections we covered functions last week. One of the sections we will cover functions tomorrow. So in either case, that is the end of the sets of slides on this. So it's here because it kind of gives you an expansion of the ideas of, the definitions that we use have to be carefully constructed, because even just exploring the breadth of the things that we define, there are already some concepts that are kind of hard to wrap your head around. Remember, Cantor took the most part of 2 decades trying to figure out that there are infinite sets that are of different sizes. And in fact, not just two different sizes. It's not just because we have countable and uncountable that makes you think there's 2 tiers. No, there's Aleph null, Aleph 1, Aleph 2, Aleph 3, and all of those are different sizes. So there's technically an infinite number of sizes. So, okay, so this is kind of here just to expand your mind on this, and it's an interesting enough topic. If you're interested enough in the kind of discussions that we have here, we're probably going to do something similar. The last part of chapter 4 is more practical than this, and it's actually something that you can definitely see the concepts of number theory in action in practice. But there is a similar concept that these are technically topics that I'm personally interested in. So, infinite sets, different cardinalities, even the incompleteness theorem from Gödel are part of what part of the realm of logic that I like looking at. So we'll see a bit more of this with logic puzzles from chapter 1. That would be technically before we have examination 1, but in the original schedule we would have had after examination 1. So I would probably have made this extend into the study break if you're interested in that kind of thing. And the summer is generally a lighter schedule. So in any case, that is the end of the slides from chapter 2. I'll be uploading this soon, and I'll look at some videos that I can also upload uh, from TED Ed and from 3B 1B. So three blue, one brown. Both of which are YouTube channels. So you can look at those videos if you're interested in looking at other related discussions. Hopefully, they're probably much better produced than this particular video. So it might be of more entertainment value or even more educational value to you. In any case, that's the end of this video. We'll go through since this is being recorded after basically the HA phase 2 has been enacted for the next month. We'll see a bit more of these, looking at slides and me writing on them as we go forward. Okay, that's it. Stay safe, stay vigilant, stay healthy. I'll see you when I see you.